everybody, and welcome to Mindset Learn Extra. My name is Pumi, and today I am joining Tracy for Physical Sciences Grade 11. How are you doing, Tracy?
Fine, and you, Pumi?
I'm good, thank you.
Welcome to the show.
Thank you.
You're a little nervous. It's the first one on your own.
Well, yeah, it is.
That's
really...
okay. You'll be fine. I'll use and abuse you. It's great.
Oh, great stuff. All right, then, guys, do remember that all what you have to do in order for you to interact with us on the show is just to like us on Facebook, ask as many questions as you can, and do remember that you can always post your random acts of fun. Yes, acts of kindness, I beg your pardon. Remember that you can always win the Simba Cheetahs. Very interesting, guys. There is the pack. You can always check it out there. It is very interesting. All what you have to do is just to stick around with us right up until the end of today's show.
Brilliant. I wouldn't want those. So if you guys don't want to post it on Facebook, I'll just take them home.
Yeah.
No, actually, that's bad. Would need to go to gym for 15 million hours. Anyway, so, guys, what we're doing today is we are looking at Newton's law of universal gravitation. This is his fourth law. This is actually quite an interesting law because it's one of those laws that you go, okay, why is it called universal? Because it's the only law, well, I wouldn't say it's the only law, but it's true anywhere in the universe. So whether you go to the moon, or you go to Mars, or you go to Jupiter, or you go to another galaxy, Newton's law of gravitation is there and is around, okay? So what we're going to do today is we're going to look at several things. We are going to describe, well, I'm going to describe and try and explain Newton's law of gravitation to you. I'm then going to demonstrate something to you, which I'm very excited, and Pumi's going to help me. She just doesn't know yet. Yeah. So anyway, that gravity, or the acceleration due to gravity, is independent of mass. Now, I know this is something we really struggle with because in your heads you go, no, mass has to play a role. It doesn't. Air resistance does. So we're going to talk about that in a little while, and then we're going to solve some problems involving Newton's laws. There will be some explanation when it comes to your calculations and that sort of thing in Newton's law of gravitation, but really a lot of this is going to be a little bit of explanation. They're proportion questions. So what happens if you double a mass and half a force and all sorts of things, and then we all know things get a little hairy because the maths gets a little hairy. So let's just go right to the beginning. So we start with the most basic concept, which is all objects are attracted to the Earth, irrespective of their shape, size, or mass. You all know, okay, if I have to, and I'll catch it though, when I have my pen and I drop it, it drops, okay? It doesn't miraculously hang in the air, and it doesn't miraculously go up all by itself. You know it's going to fall. If I throw it up, which I won't do either because the person who looks after the TVs will hurt me, okay, and I don't want to do that because he's a big man. But if I have to throw it up, the pen will go up for a little bit, and then eventually it falls down. We all know that, okay? And if your name's Tracy, you know you fall down quite often as well because I'm quite a klutz. Yeah. So, you know, I fall off stairs, and we all know we fall. It's one of those things. We understand that. Yeah. But what does that mean? That means there is a force of attraction between the Earth, okay? So that's where we're starting with. Starting point is the Earth and any object. But there's an important fact here, that there isn't just an attraction between the Earth and any object, but actually there is a force of attraction between any objects. It doesn't matter. It doesn't have to be between the Earth and the object. That's there. We experience that force of attraction because the Earth is so big. Okay, so the force that the Earth pulls on us is really big. So we experience it more. But even that annoying boy in the class who sits next to you, who, when you sit in your science lesson, instead of listening to a teacher, all you're thinking is, I just want to slap him, which you can't do. There's actually a force of attraction between you two as well. And now I can just hear lots of screams at home going, no. And you know what, even worse, there is actually a force of attraction between you and your books. Granted, it's very small.
It's very important.
Very important.
Very important.
Anyway, it's very small, but there is a force of attraction. Okay? That force of attraction is very, very important. That can be described to us in Newton's law of universal gravitation. This is a definition, grade 11s. You must learn it. And Newton's law of universal gravitation says to us, the force of attraction, first part, not the force of attraction. Force is a vector. That means I have to give direction. Attraction is direction, okay? So the force of attraction between two objects, and this is between any two objects in the universe, which theoretically means there is a force of attraction between you and the moon. But remember, the moon is so far away from us right now that really that force of attraction becomes so small it doesn't play a role in our lives, okay? And that force is directly proportional. Remember, directly proportional means that if the force increases, something else increases. And what is that something else? It's the product of their masses. So now you're saying, hang on, wait, Tracy, at the beginning of the lesson, you said you were going to prove to us that the force of gravitational acceleration is independent of mass. But now you're telling us we need to put mass in. You need to hang fire for that one. But it's directly proportional to the product of their masses. Product means multiplication. And inversely proportional. Inversely proportional means if one thing goes up, the other goes down. Okay? To the square, you square it, of the distance between their centers. That last part of the statement is very important, grade 11s. Often, when we see this, we get the first part right, and then we get this inversely proportional to the square of the distance between them. We can't do just the distance between them. When we're considering something like the force between myself and the Earth, you've got to remember the Earth is ginormous. So we take it from the center of gravity, okay? But because here, with Newton's law of universal gravitation, we're really dealing with it on a very big macroscopic level. So we're dealing with big objects. It's still valid on a microscopic level. So this plays a little bit of a role in terms of bonding and intermolecular forces, but they're such small masses that it's not, we don't often consider it as being that important. But in terms of big objects, very, 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 very important. You take it from their center, okay? Which then means when you're looking at questions, be careful, because often questions that involve the Earth, they'll tell you that something gets moved to, say, 2 radiuses above the Earth, and then we forget about the radius of the Earth in the first place. When it's between people, take the distance between them, and we're fine. Okay, so what does this look like as an equation? And this is, here it is. Ooh, extend my page. Force of attraction F is equal to G, new G, it's not acceleration due to gravity, times mass 1, mass 2, divided by r squared. So F is force, and force is measured in newtons, okay? This is always force of attraction, never, ever, 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 ever going to be repulsion. So we don't need to worry about that. G is a very important constant, okay? G is known as the universal gravitational constant. Okay? Why is it universal? Because as far as we know, you never know, once we start exploring space and start living on other planets, maybe we'll find it's not true anymore. This is valid anywhere in the universe. Okay? It is a constant. That means it has a value. Lucky for you, the value is given on your information sheet. I'm hoping it's not too new for a lot of you, but it's equal to 6,67 times 10 to the minus 11 newtons per kilogram squared. I think I've got those the wrong way around. Let me just check. Yes, that's what I thought. Okay, let's just quickly do this. It's newtons. No, that one. meters squared per kilogram to the minus 2. The meter squared and the kilogram to the minus 2 gets cancelled out as we go along, so it actually is the one that gives us the newtons, all right? Where does this come from? Lots and lots and lots and lots of experimentation, okay? Lots of experimentation. And in fact, I just wanted to show you something. And I have to thank John for this, but Bill Bryson, he's one of those wonderful writers who writes all sorts of things, and he wrote a book called A Short History of Nearly Everything. Okay, it's one of those books where you read it and then forget everything, but he's just amazing at what he wrote. And basically, he's looking at the history of the world and scientific experiments and thought and things that have changed. And of course, everyone wanted to prove Newton's laws, and comes to Newton's law of universal gravitation. And then along came some, I think they might have been Spanish. I can never tell. I'm really bad with names, so I'm going to butcher some names right now. And these scientists came along, and it says here, they worked for a decade, 10 years, on trying to work something out, and then somebody else beat them to it.
Whoa.
That's just got to be upsetting. That would do it for me, but moving on. Anyway, now, what Newton conjectured, in other words, what he said could happen, and these guys actually set out to prove it, was this. He said in his books that if a plumb line, which is just a line that we hang similar to a pendulum that tells us whether something's straight, and they conjectured that if it was hung near a mountain, okay, that it would incline. In other words, it would bend slightly towards the mountain. Mountain's got a big mass, okay, and it's affected by the mountain's gravitational mass as well as the Earth's. That's just freaky if you think about it, okay? So, if they measured, and they said, if you measured the deflection accurately and worked out the mass of the mountain, you could calculate the universal gravitational constant. That is phenomenal. That just actually blows my mind, okay? They did this all over the world, by the way, and they went around the world trying to find great mountains to do it with, because they also realized the shape of the mountain, whether it was regular or square or that sort of thing. They even came down to South Africa to use Table Mountain for a while, just to see, because we know we love our square mountain, okay? But they realized somebody else beat them to the answer on that one. That's a bit scary. That would just kill me. Anyway, moving on. So, not only did Newton prove this through experimentation and extremely complicated maths for his time, it's been proven in the last couple of centuries, in the last century, which is amazing for me. M stands for mass. Mass must be measured in kilograms, and R is the distance between their centers, which means it's got to be in meters. So how do we use this? Let's quickly tackle a question, and then we'll take a break. Very typical type question that you could get. Says to us, calculate the magnitude size, okay, of the force between a box of mass 100 kilograms. So let's write that in as mass 1, okay, and a person, let's make that mass 2, of 75 kilograms if they are 0.5 meters apart. Grade 11s, you have to make the assumption that because they didn't say between their centers, that's what they mean. Okay, don't get all picky about this and go, I can't answer the question because I don't know if it's between the centers. Just make that assumption. The only time it becomes incredibly critical that it's between the centers is really when we're looking at planets and big objects. This, we assume it's between their centers, okay? What is that? This is actually not bad because now we have to calculate the force. So all we need to do is substitute it in. Okay, now I'm going to do it underneath. I would do it next to it on a page, but it's just that gravitational constant's so big. So, F, don't forget to put your equation, mass 1, mass 2, R squared, okay? Gravitational constant, 6,67 times 10 to the minus 11. Mass 1 was 100. Mass 2 was 75, and it was 0.5 meters squared. Calculator work, so important. Let's just see what this would look like on the calculator, okay? So we're going to go, and it's in maths display. I'm going to show you some stuff. 6.67. We use the exponent button to the minus 11. We're going to times by 100 times by 75. Now, I know some of you might have been taught to use brackets and stuff. I prefer to do it this way because I know you guys get confused where all the brackets should go. So now we go equals. So that's my top line answer. Don't write it in. Now we're going to divide that answer by 0.5 and square it. Oh boy. If we look at that answer, it's got millions of noughts. Please, you don't have to write it. I would prefer you to write it in scientific notation. So make sure you can change your calculator. So watch, I'm going to do it for you. We're going to go Shift, Setup, Mode 7 on this calculator, and I'm going to go to 3. Can you see it already in scientific notation for me, which is brilliant. So this is 2,00 times 10 to the minus 6 newtons. That is so tiny. Not a chance I'm going to feel that. Okay? So don't go anywhere because we're going to do an experiment when we get back.
Yay, how exciting. Yes, guys, we are going to be doing an experiment when we come back. Let's take a break. Welcome back, guys, from an ad break. I hope that you have a glass of water with you. And yes, this is going to be my favorite part of the show because we are definitely going to be doing an experiment with Tracy. Do remember that if you have questions or comments, or what you have to do is just to like us on Facebook and obviously comment and question whatever that you have with us. And of course, you can always follow us on Twitter and interact with us. We are there at Learn Extra, or you can you also have to post your random acts of kindness. Yes, that's what it is. So all what you have to do is just to stick around with us because Tracy is just going to take us through the experiment. Stick around.
Oh, thanks, Primi. Okay, guys, so now we get to the fun part. I love it. So what we're going to do, all right, is the demonstration. This is our basic question. Is the acceleration due to the force of gravity that a body experiences determined by the mass of the object? In other words, what we're asking is, does the rate at which an object falls does it depend on its mass? So if they had to take someone little like Pumi and someone big like me and throw us off a building, would I fall faster?
Yes.
You think so?
Because of the mass, maybe?
Because of the mass.
Yes.
Yeah, that's what we think. We sort of get that, and then we sort of go, hang on, wait. But if we think back to our equations of motion that we learned in grade 10, and we go, no mass in those equations. Oh, there's got to be something in it. So that's what we're going to look at, okay? What we've done, and I've set it up already, but I just want you to see the diagram, okay, is I have a retort stand with a clamp, and I've got a piece of string with mass pieces. And what I'm going to do is I'm going to change the mass of the mass piece. Keep everything else the same. So I'm going to swing the pendulum, and we're going to look at how fast it swings. Now, as multitask ability that I have, I'm actually going to ask Pumi to take our data down so that when we get to the results, which we'll get to afterwards, and we can compare them nice and quickly, Premier's going to have all the values for us because we want to make sure we do this correct, okay?
Yes.
So, and it should work because I did this last night, but you know how things go. So, what do we have? As I said just now, we have our retort stand, and it's in my way, but it's okay, with my mass pieces. What's very important here, though, grade 11s, is that I can't take I could use any shape mass piece as long as when I'm changing the mass piece, I keep the shape the same, okay? So I can't go and, at the moment I've got 3 little mass pieces on this, it's got 30 grams. I can't change this for a 50-gram big mass piece that says the shape of my pen. What changes then is the surface area, and surface area most definitely plays a role, okay? You've looked at Newton's laws, you know that there's things like air resistance and friction, that becomes a problem. Obviously, this experiment is going to have some flaws in it, but it's actually a really good one. Important with any experiment, grade 11s, is we keep our controls. Our controlled variables are going to be the height from which I swing the pendulum, number one. Number two, it's going to be how many times I let it swing when I take the time. Okay, so those are important controls. The things, my independent variable, the thing I'm going to change is the mass, okay? And I have lots of mass pieces. Don't worry, we're not going to use all of them because I don't need to. So I'm going to keep another control, I'm going to keep the type of mass piece the same, but I'm going to change the number of mass pieces, which means I'm changing the mass. The dependent variable is what I measure. Now that's going to be unusual because in this one we're measuring time, and we're going to use the time as an indication of acceleration. A lot of the time, grade 11s in your experiments, time will be your independent variable, not for this one. So what we have here is I have my stopwatch, okay, and it's a nice big one because, you know, we're getting old. And I have, I'm just going to leave this here as my marker, so my ruler is going to serve as my indication for my height, okay? So I'm going to drop, there we go. Can you see it's that's the height I'm going to go from every single time. So there's the height, hopefully I haven't changed it. Also, when I just want to show you, this is going to drop. I'm only going to start timing when it reaches here. Okay, that's where I'm going to start timing. Then we're going to let it go to the side. It's going to come back here. It's going to drop height a little bit, and then it's going to, that's one swing. And I'm going to measure it 5 times, because after 5 times it starts to get a little fast. Well, it's harder to see. You can't just measure the first swing because it's so quick. And remember, one of the things for experimental error is going to be my reaction time on getting the stopwatch to work. And I'm using my tablet before the stopwatch because a handheld stopwatch is actually quite difficult, and just it gets, yeah, I'm seriously testing my ambidexterity. I think that's the word. It's the reason why I don't teach you guys English, eh? That's why you have specialist English teachers. In fact, my children at school laugh at me all the time. I've agreed, I will teach them science, they can teach me English. So, all right, are we ready? Okay, now I do need to just be here because I need to see when it gets to the middle. So let's go. So, and it starts and it went, so that's 2, 3, 4, 5. Oh, okay, so for me,
yes,
that first reading is 6.7 seconds.
6.7 seconds.
6.7 seconds, okay?
Okay.
Let's increase the mass. Now we're going to make it 50 grams. So I'm putting 5 mass pieces on, okay? So we're going to put 5 mass pieces on. And now the theory is, if acceleration due to gravity is determined by mass, and now it's heavier, this should take quicker to do the same thing because it should accelerate faster, okay? So we're going to keep it at the same height. Okay, there we go. I'm going to try let it go so that it goes straight, but there's no guarantee. All right, are we ready? Let's, oh, I need to be here. Sure, can you imagine what it's like doing experiments in my class? Okay, and there we go. And it's gone skew. So that's 2, 3, 4, 5. And guess what?
Did it decrease?
No, it's 6.7 seconds.
Oh.
I kid you, I would show you, but I pressed the laptop. I promise you it's 6.7.
Wow, so it's the same as the first one?
Same one.
Whoa. Okay.
Now that could have been a little bit of an oopsie maybe. Maybe. So let's do it again.
Okay.
But now we're gonna increase the mass again. So let's go to, now I had 5, so now I put another 2, so that makes it 7. Okay. So this is trial number 3.
Number 3.
Okay. So now we have 70 grams. Now this really should be, if we're going to get to the right one. So there we go. Okay. We're going to reset, and let's go from here. Okay, and 1, 2, 3, 4, 5. Okay. Ooh, that one was 7.6.
7.6 seconds.
Okay. Oh, that's because I can't count. We have a wonderful director.
Whoa.
She just told me it swung 6 times. I hope you guys picked that up. Apparently I can't count. Thank you, Belinda. All right, so
Okay.
now, you know what? That's great because at least we know what the error was.
Yeah.
But if this happens, because of course it happens, we luckily got told straight away exactly what I did wrong, which is great. But if you do an experiment like this and then you put more in, and now you get the next one, say to be 6.7, 6.8, 6.9, and you go, but now why was that one so far out? It's experimental error. The best thing, if you can, if you have time, is to go redo that one. Okay, go do it again, and maybe you get it, there's something about it that makes a difference. Then you start to look at it, okay? Oh, stop. Then you start to look at it, and you start to discuss why that 1 point doesn't lie on your graph that you draw, or doesn't quite match up all the things you were saying. So just it happens, okay? You all do that. I mean, that was, neither of us actually noticed. Apparently, I can't count to 5. Anyway, 5's a big number for some of us. But thank you, Belinda. That's why we have directors. Okay, so should we try that again?
Yes, let's do it.
Okay, let's make sure I get 5 this time, hey? And here we go. 1, 2, 3, 4, 5. There we I think, no, that was 6 again, apparently.
Wow.
Because I got 7.8 that time.
Oh.
Wow! Okay, I'm really struggling with this
So
counting
are we
thing.
starting it over again? Or?
Let's try this one once more. If I
Okay.
can't count to 5 this time, then you know what? Seriously, we're moving on. But this is live television and live experiments.
I will forgive you. Mistakes do happen.
I am human. Don't tell anyone, especially not the kids I teach. Okay, let's try again. Okay. Ooh, and I started in the... I didn't start
Okay.
that. You know what? Leave that one at 7.8. I'm going to add 2 more. Let's see if it works if I use 9. Okay. We'll come back to the 7. Because we do have time constraints, unfortunately. Okay, so here we go. It's at the right height. And 1, 2, 3, 4, 5. Ha! No, that was 6 again.
Whoa.
Anyway, but actually it's fine because that one went 6 and we got 7.4, so it's fine.
Okay.
Write it down because we got 7.4 and that was, so I've done, this is not, I'm doing it.
So what is the best now? I mean, the
That
time?
was 9.
9.
So now we're going to do one more with 11 and watch, I'm going to count at 6. I don't know what it is with this number 5. Okay. I'm also running out of space on my little hook for my mass pieces, so... Okay, let's see if we can do this. Okay, there's 1, 2, 3, 4, 5. No, that was 6.
That was 6. Okay.
That was 6. And we got 7.4.
Mm-hmm.
Okay, before I embarrass myself anymore, we got a good enough result. It's fine. So, follow me to the board because we're just going to move on because we do realize I'm very challenged, apparently, today. So, let's just remind ourselves, oh, I only did 4 trials, but we did it 5 times. It's okay. So, just for us, so we remember that for the first 2, we swung it 5 times. Okay. And there's a big box over here. And for the second 2, we did it 6 times. Okay, you guys, we're okay with that. So, for the first 2, what was the first time that we got?
We got 7.4. Is it?
No, number 1, the
Number
first
1,
try.
6.7.
6.7. And then for the second one?
6.7.
We did, because I could count to 5 then.
Yes.
Then for the next 2?
7.6.
7.6. And then?
And the last one was 7.4.
Okay, it's close enough. Now, guys, this is what I want you to see. Besides the fact that I can't count, so we understand that, and I do apologize. These times for the swings are pretty much the same when we let it swing the same time. That tells us that the pull that gravity has, because remember, gravity is going to speed it up till it gets to the middle. Then it keeps swinging. Gravity will slow it down till it stops. Then it speeds up. Then it slows down. Okay, so the direction. Now, if the acceleration is the same, so the force it experiences is the same, the acceleration due to gravity, that time is the same, because it's going to cover the same distance. So what this time tells me is that acceleration due to gravity has absolutely nothing to do with the mass of the object. Okay, which is what I wanted to have as the conclusion. Anyway, but yes, I'm not sure anyone can hear me right now. There we go. Now, my conclusion is a huge, big blank block, which should be mass is independent. Let's do this. Your conclusion is that acceleration due to gravity is independent of mass. We've proven this experimentally. Let's prove it mathematically. So I'm going to show you something. So we're going to do this quick, because you can get asked to do this. You know that weight is mass times gravity, m times g. We're okay with that. We also know the force of attraction between two objects is the mass squared times divided by the distance between them squared. What I'm doing here, m is the mass of my object, mp is the mass of the planet, in this case Earth, and r is the distance. What we need to recognize here is the weight that we feel, Fg, is the force of the Earth on us. It is the force of attraction between us and the Earth. Newton's second law is exactly the same force. So that means that Fg is equal to F. Okay? That means if I take the F's away, writing what we know, mg equals g mp over r squared. Now we do a little bit of math trick and we go, well, I have the same mass on both sides. That means they cancel out. Now watch here. G is equal to big G times the mass of the planet divided by the distance squared. Okay, and this is actually the radius of the planet. So we're assuming we're standing on the surface. What does this tell me? Acceleration due to gravity is only dependent on the mass of the Earth or the mass of the planet and the radius of the planet. That's how we can find out the acceleration on the moon, because they've actually been able to work out the mass of the moon and the radius of the moon. G is our universal constant, 6.67 times 10 to the minus 11. Okay? Please be careful. Nice question. What is the difference between little g and big G? Little g is variable, changes from planet to planet. It's a version of acceleration, okay, and is measured in meters per second squared. Big G is a universal constant, stays the same no matter where you go in the universe. 6.67 times 10 to the minus 11 newtons, meter squared per kilogram squared. Okay? All right, so after that very embarrassing moment, I think it's time for me to have a break, and then we'll come back and do some problems.
Yes, most definitely, guys. It is now time we take a quick break, but do remember that you can always like us on Facebook and ask us any questions that you would love for us to answer you. Tracy has put a smile on my face. Remember that if you would love to you can always try and post the random act of kindness, yes, random acts of kindness on Facebook. You can stand a chance of winning the 5 awesome CDs that we have, and of course the Cheetos and the pens, and also the Mindset Learn Extra t-shirt. If you would love all of that and more, please put the random act of kindness with you and your friends. We'll take a break and we'll come back right after this. And welcome back, guys, from an ad break. We're all still with Tracy doing Newton's law of gravitational acceleration. Very interesting show indeed. Please do post your questions on Facebook. It is facebook.com// Learn Extra, or interact with us on Twitter. It is Learn Extra. I would love to have all of your questions, because we are prepared to answer all of your questions, because Tracy is with us taking us through this interesting topic for the day.
Thank you, Bumi. Sham, I think I threw you into the deep end then. Anyway, well, let's move on. Let's get to the part which I know I can do without actually killing anyone or counting to 6 instead of 5, whatever.
Yeah.
Anyway, so the point is you got that acceleration doesn't matter. The mass is irrelevant to acceleration due to gravity. Now what we're going to do is we're going to do some problems. Now I've taken them. The nice thing is this has been in the curriculum for hundreds of years, just about, that's what it feels like. So if you can actually get hold of old question papers from 10, 12 years ago, nice Newton laws questions, nice Newton's laws of gravitation questions, such a good place to find practice questions, okay? So I've actually taken the question papers from 2001 and 1999, okay? Some of you hopefully were born then if you were in grade 12, if you're in grade 11 already. And what we're going to do is I'm going to show you how to do a couple of questions which we call proportion questions. And these ones can, and ratio questions, these ones can get a little hairy. So I do it in a slightly different way because we need to make sure that you get the marks for a question like this. Often they're multiple choice and they start to do all sorts of weird and wonderful things and you look at them and you go, but there are no numbers. That's okay. Let's look at the first question. It says, the distance between two similar mass pieces, so they're saying to us right at the beginning, is that the masses are the same, or thereabouts, is r. So the distance is r, and the magnitude of the force they exert on each other is F. I'm going to do this in arrows. So in other words, their force between them is F, is G, mass 1, mass 2, over r squared. Now, I don't know mass 1 and I don't know mass 2, but that doesn't matter. We're going to see now what they're wanting. And I'm going to change pen so it's a little bit easier. If the distance, so if r is halved, so they're saying to me I'm now going to use half of r, and the mass of both objects, both of their masses, is also halved. So in other words, I have 0.5 of the first mass and I have 0.5 of the second mass. What is the magnitude of the force they now exert on each other? They want this in terms of the original force. So what they're asking you is, by halving the distance and their masses, what have we doubled the force? Have we tripled the force? Have we halved the force? What have we done? How does the force change? This is where we've got to be careful. Your teachers, and there's nothing wrong with it, perfectly fine, might teach you to do this with a proportion, okay? Go, well, force is directly proportional to mass. It can just get a little complicated. So what I want to show you is a little bit of a trick where you look for something you know. That's my trick. So watch what we're going to do. My new force is G, okay, times my new mass, which is half of the original one, times my other new mass, divided by my new distance squared. Stay with me. Now we go, okay, let's put all the constants, the numbers, together. So we're going to go, so we're going to put all the variables on one side of the fraction. We're going to put all the constants together. So we're going to go, okay, this is 0.5 times 0.5, which is 0.25. Because remember, this is multiplication. It can be in any order. It doesn't make a difference. G, M1, M2. Now, it's 0.5 r squared, so 0.5 is also squared, and 0.5 squared is 0.25 r squared. Now we work out what the numbers would give us if we just had them, and this one's actually quite nice because we've got 0.5 divided by 0.25 divided by 0.25, which is 1. Okay, so we have 1 times G M1 M2 over r squared. Now I'm hoping someone is looking at this going, oh wait, Tracy, I see it. Actually, maybe I do want to move this aside. Watch here. Doesn't G1, and isn't that G M1 M2 over r squared what I've got over here? So doesn't that mean that actually the force is the same? That my new force, because I've got this, board doesn't like 2 instructions at once. I have that being the same over there. Look for something we know. So in other words, my new force is equal to my old force. So by halving the masses and halving the distance, we actually cancelled out the differences. Okay? Stay with me. Let's do one more. That's like this one. This, they love these ones. Love them. Because now it gets a little bit less, how does that work? Watch here. They say to us, a large planet. You know, they're just trying to make it sound exciting. A large planet has a radius 10 times that of the Earth. Radius is 10 times the Earth's. So the radius of my planet is 10 times the radius of the Earth, which I'm going to call RE so I can remember it. It has a mass 300 times that of the Earth. So my planet's mass is 300 times the mass of the Earth. And it's round about here that we start to go, but Tracy, I don't know the radius of the Earth, and I don't know the mass of the Earth. It's okay. They don't expect you to know them. If you are expected to use the actual values in a calculation, either you are going to have to work one of them out, and they'll give you the other, or they will give them to you. Don't worry about it, okay? Because I'm going to show you. I'm going to do the same things we did in the last question. However, if the weight of the body is 500 newtons on the Earth, okay? If G is 500 newtons on the Earth, what is his weight on the planet? In other words, they're saying to you, if the force of attraction between the body and the Earth is 500, he now goes to another planet, which is 10 times the radius, 3 times the mass. What is his weight going to be there? Not quite, the numbers aren't quite as nice as the last one, because they're not going to cancel each other out, but we're going to do it step by step. The 500 newtons is the force of attraction between the Earth and the person. So we're going to do this. So that's the force of the Earth, and it's G, the mass of the object, which we're not going to worry about, the mass of the Earth divided by the radius of the Earth squared. We're all okay with that. Let's deal with the planet. I'm going to do it in another color so you can see what I'm doing. So the force that he's going to experience on the new planet is G, mass of the planet divided by the radius squared, because I called it big R. But that's not going to really help us. So we want to get it in terms of mass of the Earth, radius of the Earth, okay? So we go over here and we say, fine. We knew that this was G. The mass of the man and the object didn't change, because that's constant, much to some of our horror, okay? It is constant. The planet was 300 times the mass of the Earth and 10 times the radius of the Earth. So I've substituted the mass of the planet, radius of the planet with values. I'm going to do the same thing I did last time. I'm going to take the value, the numbers to the front. So I've got 300 times G, mass of the Earth. 10 squared is 100. Sorry, wrong R. So this is 100 times RE squared. Now watch here. This is the same as that. It's the same value. That, from the Earth, is 500 newtons. They told us the mass, the weight on the planet was 500 newtons. So now we go, oh wait, they're the same. We know the value of that set. So what we can do here is we can go, okay, fine. 300 divided by 100 is, hopefully you're screaming at the TV now going 3. Of course it's 3. This whole part that I've circled is worth, well, it has a value of 500. So now we have 3 times 500, which is 1,500 newtons. So even though he's going to a planet which is ridiculously big compared to Earth. 300 times the mass, 10 times the radius. His weight will only be 3 times bigger. Okay? What you also need to recognize is radius makes a huge difference here. Okay? It's very, very important about the radius because we square it. So small changes in distance make a big change in force. What am I telling you need to do here, grade 11s, okay, is with ones where they change things and they go 3 times this, 2 times that, half this, quarter that, all of those sort of things, it becomes a little bit of an English nightmare, I understand that. Find something you know. You are always going to have something you can compare it to. That's the important thing here. Find something to compare it to, okay? Last question. And notes. Yes, it is. I think. I actually have one after this. The radius of the Earth is 6,4 times 10 to the 8 meters. That's your job. Okay, so radius of the Earth is 6,4, in fact, I will make this the last one, times 10 to the 8. Its mass, which they call big M, like I said to you just now, they'll give it to you if you need it, is 6,00 times 10 to the 24 kilograms, so this was in meters. Now it says, use Newton's law of universal gravitation to calculate the acceleration, not what I asked you, of a 10 kilogram object near the surface of the Earth. That 10 kilogram is irrelevant. I didn't want the force of attraction between the Earth and that object. I wanted the acceleration. So that equation we found earlier, acceleration, G, mass, in this case they said big M, so I must just write it as big M, G, M, and they said this was, they didn't give me the radius, so let's use, I put it as R squared. Straight substitution. So it looked hard. I have to write a little small if I want to fit this all in, but it's not really. Okay, 6,67 times 10 to the minus 11. The mass was 6 times 10 to the 24. Radius is 6,4 times 10 to the 8. So let's just actually calculate it. So we've got 6.7 to the minus 11 times 6 exponent 24. That equals, and we're going to divide that by 6.4 to the 8 all squared. And look at that. Okay, that doesn't look like it's the right number though, because I did square it. There's something wrong with my numbers, but it's okay. You write it down as you're given. Ooh, sorry. It was 9,81 times 10 to the minus 4. I think I typed something wrong when I typed this question, but that's okay. We got 9,8 in the region. Yes. I'm actually convinced I did something with the mass, so don't stress about it. I've got 1 minute. Okay. Quickly. An object falls towards the Earth because the force exerted by the Earth on the object is greater than the force exerted by the object on the Earth. Is the statement true? No. Why? This is Newton's third law. Yes, we fall to the Earth because the Earth has more inertia. Okay, it's part of gravitation. Both of us are attracted to each other. I attract the Earth attracts me. I move because I'm smaller. I have a smaller inertia. It's easier for me to move. Could you imagine if we all tried to move the planet? That would just be ridiculous. Okay? No, it is not true. We attract the Earth with the same force. The force attracts us. The Earth doesn't move because the Earth has a greater inertia. Okay? And on that note, I need to say goodbye. Pumi, I think you've done a wonderful job.
Thank you.
Welcome to the Madhouse. And we'll see you again soon, I hope.
Yes, hopefully.
Good.
Hopefully. Thank you, okay. Guys, that was Tracy right there with physical science. Very interesting. Remember that if you missed today's show, do not worry because we do have a page where you can actually go and download the notes. Please go to learnextra.co.za/live. That is where you can download the notes, the videos, so that you can keep up with what we did today. Or you can always interact with us on Twitter. That is @LearnExtra. Then you can ask questions, we can always talk, and of course on Facebook, that is facebook.com/LearnExtra. That is all for today. Thank you so much for joining us. This has been Mindset Learn Extra. Thank you, grade 11s. Bye-bye.
the force of attraction. Force is a vector. That means I have to give direction. Attraction is direction, okay? So the force of attraction between two objects, and this is between any two objects in the universe, which theoretically means there is a force of attraction between you and the moon. But remember, the moon is so far away from us right now that really that force of attraction becomes so small it doesn't play a role in our lives, okay? And that force is directly proportional. Remember, directly proportional means that if the force increases, something else increases. And what is that something else? It's the product of their masses. So now you're saying, hang on, wait, Tracy, at the beginning of the lesson, you said you were going to prove to us that the force of gravitational acceleration is independent of mass. But now you're telling us we need to put mass in. You need to hang fire for that one. But it's directly proportional to the product of their masses. Product means multiplication. And inversely proportional. Inversely proportional means if one thing goes up, the other goes down. Okay? To the square. It's one of those little issues that go, okay, why is it called universal? Because it's the only law, well, I wouldn't say it's the only law, but it's true anywhere in the universe. So whether you go to the moon, or you go to Mars, or you go to Jupiter, or you go to another galaxy, Newton's law of gravitation is there and is around, okay? So what we're going to do today is we're going to look at several things. We are going to describe, well, I'm going to describe and try and explain Newton's law of gravitation to you. I'm then going to demonstrate something to you, which I'm very excited, and Pumi's going to help me. She just doesn't know yet. Yeah. So anyway, that gravity, or the acceleration due to gravity, is independent of mass. Now, I know this is something we really struggle with, because in your heads you go, no, mass has to play a role. It doesn't. Air resistance does. So we're going to talk about that in a little while, and then we're going to solve some problems involving Newton's laws. There will be some explanation when it comes to your calculations and that sort of thing in Newton's law of gravitation, but really a lot of this is going to be a little bit of explanation. They're proportion questions. So what happens if you double a mass and half a force and all sorts of things, and then we all know things get a little hairy because the maths gets a little hairy. So let's just go right to the beginning. So we start with the most basic concept, which is all objects are attracted to the Earth, irrespective of their shape, size, or mass. You all know, okay, if I have to, and I'll catch it though, when I have my pen and I drop it, it drops, okay? It doesn't miraculously hang in the air, and it doesn't miraculously go up all by itself. You know it's going to fall. If I throw it up, which I won't do either, because the person who looks after the TVs will hurt me, okay, and I don't want to do that because he's a big man. But if I have to throw it up, the pen will go up for a little bit, and then eventually it falls down. We all know that, okay? And if your name's Tracy, you know you fall down quite often as well, because I'm quite a klutz. Yeah. So, you know, I fall off stairs, and we all know we fall. It's one of those things. We understand that.
Yeah.
But what does that mean? That means there is a force of attraction between the Earth, okay? So that's where we're starting with. Starting point is the Earth and any object. But there's an important fact here, that there isn't just an attraction between the Earth and any object, but actually there is a force of attraction
Hello everybody and welcome to Mindset Learn Extra. My name is Pumi and today I am joining Tracy for Physical Sciences Grade 11. How are you doing, Tracy?
Fine, and you, Pumi?
I'm good, thank
Welcome
you.
Welcome to the show.
Thank you.
You're a little nervous. It's the first one on your own.
Well, yeah, it is.
That's
really
okay, you'll be fine. I'll use and abuse you, it's great.
Oh, great stuff. All right then, guys, do remember that all what you have to do in order for you to interact with us on the show is just to like us on Facebook, ask as many questions as you can, can. And do remember that you can always post your random acts of fun. Yes, acts of kindness, I beg your pardon. Remember that you can always win the Simba cheetahs. Very interesting, guys. There is the pack. You can always check it out there. It is very interesting. All what you have to do is just to stick around with us right up until the end of today's show.
Brilliant. I wouldn't mind those. So if you guys don't want to post it on Facebook, I'll just take them home.
Yeah.
No, actually, that's bad. Would need to go to gym for 15 million hours. Anyway, so, guys, what we're doing today is we are looking at Newton's law of universal gravitation. This is his fourth law. This is actually quite an interesting law because between any objects, it doesn't matter. It doesn't have to be between the Earth and the object. That's there. We experience that force of attraction because the Earth is so big, okay? So the force that the Earth pulls on us is really big. So we experience it more. But even that annoying boy in the class who sits next to you, who, when you sit in your science lesson, instead of listening to a teacher, all you're thinking is, I just want to slap him, which you can't do. There's actually a force of attraction between you two as well. And now I can just hear lots of screams at home going, no. And you know what? Even worse, there is actually a force of attraction between you and your books. Granted, it's very small.
It's very important.
Very important.
Very important.
Anyway, it's very small, but there is a force of attraction. Okay? That force of attraction is very, very important. That can be described to us in Newton's law of universal gravitation. This is a definition, grade 11s. You must learn it. And Newton's law of universal gravitation says to us, the force of attraction, first part, not the force